Okay, so hello and welcome all to the interactive live sessions, the first week of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I will be the teaching assistant for this course. So this is how it will work. So every week uh, there are new video lectures being uploaded. You will hopefully you are going through all of them, and every week on Tuesdays from 6 to 7 or 6 to 8, whatever in this time frame we will meet, and we shall discuss some problems together, which I'll be preparing in the form of slides. They're mostly MCQ type of questions and some numericals as well. Uh, these will be pertaining to the last week's lectures. So today we will go through week one lectures, and similarly we will hold each session for 12 weeks of this course. And in the end, we might have another session where we revise all the concepts before the final exam of this course. So that's how things will work, and you can uh, you know bring up any doubts or any remarks about the lectures or anything pertaining to this course. This is the best place to discuss it. The lectures are one directional, that is, the professor lectures and you listen to it, but these sessions are aimed to be as much bidirectional as possible, so that you can you should participate in these discussions as much as possible. So without further ado, let's get started. So uh, let's have a look at the first question of today's session. It is an MCQ type question which is asking us that to select the correct definition of convection, and then there are three statements given below. So one of them describes the correct definition of convection in its truest sense. Once you have read all these statements and made a choice that this should be the correct answer, you can either type in the chat box or you can unmute and answer as well, whichever way you feel more comfortable. And then we will look at the answer and have some discussions pertaining to it. So the statements given for this question, or the options given for this question, are option A, heat transfer by the bulk movement of molecules within fluids; option B, heat transfer by microscopic collisions of particles and the movement of free electrons within a body; or option C, heat transfer through electromagnetic radiation. Which of these statements gives the correct definition of convection? Okay, so we have a quick response in favor of option A. Let's hear what others have to say. Once again, I will like to repeat the importance of participating in this, because these are supposed to be as interactive as possible. So don't feel shy. There's no or be scared that I might pick the wrong option. There's nothing like that. We are all here to learn. So, but participating is important. So, first, read the question carefully and all the options carefully. And once you have picked a correct option, uh, please type in the chat box or you can answer. So we have two responses in favor of option A. Let's look at the solution now. It is indeed option A, so you're all correct. So heat transfer by the bulk movement of molecules within fluids. So that's what describes convection. Now before going into it, let's go through the other two options. So option B says that it's the heat transfer by microscopic collisions of particles and movement of free electrons within a body. Can anyone tell me what kind of uh, mode of heat transfer is it? It's something other than convection, but what is it? Yeah, correct. So it is conduction. So in conduction, what happens is that this mostly it is the primary mode of heat transfer in solids, but then again conduction can happen in other states of matter as well. So for that matter, it happens in fluids as well as gases. liquids as well as gases. But the physical way it happens is that there is a lattice of multiple particles. So I'm only drawing one layer, and these particles, they all vibrate with some amplitude and frequency. And what happens is that heat energy in its most fundamental form is nothing but the sum total of the kinetic and potential energies of these particles. So if we heat one side of this body, what that essentially means is that we are increasing the vibrational energies of these particles, and that gets transported from one particle to the next, and in this way heat is transported through some medium, and that physical mode of heat transport is called conduction. There's another mode as well, which is through electromagnetic radiation, and the name itself contains the word radiation, which is the other mode of heat transfer. So in this case, what happens is that there are electrons orbiting uh, a nucleus for every single atom, and when those electrons, they go from a higher energy level to a lower energy level, they emit something known as a uh, light energy photon or anything. In this case, these electromagnetic radiations are in the infrared region. So that is what comprises of, sorry, infrared. So these are the wavelengths in which mostly heat is transported. So that's what entails radiation. And the main focus of our course would be convection, which is through bulk movement of molecules within fluids, or the fluid mass itself. So we will go through several examples in detail of this, but mostly what it means is that if there is some surface which, you know, if it is at a higher temperature, let's say T wall, which is higher than T infinity, which is the which is the temperature of the fluid surrounding it. So then what happens is that molecules of this fluid comes near this, gets heated, and these molecules get transported as well, and newer molecules also come in contact. So heat is being transported by these molecules. They can bring in heat, they can take away heat. It all depends on the temperature gradients, temperature differences. But this is the main fundamental difference of convection from the other modes, conduction and radiation. So we will go through much more details of this throughout the course. So any questions on this so far? If not, we will move along. We'll move on to question number 2, which is telling us that the grad of V equal to 0 can be written as the continuity equation under which conditions? Is it for option A, steady incompressible flows, option B, unsteady incompressible flows, option C, both A and B, or is it option D, none of the above? Sorry, not grad of V, divergence of V. So V is a vector. Let me define this first. So the vector V is nothing but the velocity vector of the fluid, which can be written like this. Sorry, which in this, so E I, U I cap plus V j cap plus W k cap. So I, j, and k, these are the unit vectors along the three normal directions, and three normal directions x, y, and z. So if this is our coordinate system, then we have x, y, and z, and I, j, k are in these directions respectively. I cap, j cap, k cap, and u, v, and w are the components along that direction. So u, v, and w. So this is what V is, and what is divergence of V? Divergence of V can be written as dou x I cap plus dou y j cap plus dou z k cap. and a dot product with this vector v, which is u I cap plus v j cap plus w k cap. Okay, so we have one quick response in favor of option C, both A and B. Now read the question and the options carefully and pick out your favorite solution, and we will look at the correct solution and have a detailed discussion. When can this expression, this equal to 0, be written as the, or would it be correct to write this as the continuity equation under which conditions? Is it for option A, steady incompressible flows, option B, unsteady incompressible flows, or option C, both A and B, or option D, none of the above? Okay, so let's have a look at the solution. It is actually option C, both A and B, because the more general form of the continuity equation is basically the divergence of rho into v vector being equal to 0. Now, rho can be a constant, which it is in the case of incompressible flows. So if it's constant, we can take it out and say, this equation then becomes this being equal to 0, and we can get rid of this and simply say that divergence of v should be equal to 0. And this is true irrespective of the flow being steady or unsteady, because rho itself is constant. It does not change with space, it does not change with time. On the other hand, if it was a compressible flow, then this wouldn't have been right. Then the correct way to write this would be in this form, where the divergence of rho into v vector is equal to 0. And that expression, expressed in its scalar form would look something like this: dou dou x of rho u plus dou dou y of rho v plus dou dou z of rho w equal to 0. Okay, so that's why option A and option B both are correct, and in this case the correct solution would be option C, which says it should be both A and B. Any questions on this? All right, so let's keep moving. We'll move on to question number 3 now. So this is asking us, Nusselt number can be thought of which of the following? Is it option A, dimensionless heat transfer coefficient, option B, dimensionless temperature gradient, option C, ratio of convective heat transfer to conductive transfer, or option C, all of the above? Okay, so we have a response in favor of option C, that is ratio of convective heat transfer to conductive heat transfer. Nusselt number, as we know, is a dimensionless number that becomes very important in problems of heat transfer, and its expression is given like this: HL by K, where H is the convective heat transfer coefficient, the K is the conductivity of the material, and L is the characteristic length scale of the problem that we are dealing with. So should it be option A, dimensionless heat transfer coefficient, option C, dimensionless temperature gradient, option C, ratio of convective heat transfer to conductive heat transfer, or is it D, all of the above? We have so far one response in favor of option C. Let's hear what others have to say. Okay, so let's take a look at the solution. It is actually option D, all of the above. So that means all these three statements are correct. Let's go through them one by one. So option A says, oops, sorry. So option A says that it should be a dimensionless heat transfer coefficient. So that's true because uh, we can write, what is happening? Sorry. So this heat transfer per unit area, or let's say heat transfer for that matter, can be written as HA. Sorry, I don't know why this technical glitch is happening. So H into A into T minus T infinity. So this is the convective heat transfer when there is a substance at temperature T and T infinity is the fluid temperature around it. Uh, and also, so this is the Q leaving this solid surface through convection. And we know that an equal amount of heat has to flow through this solid as well, which is given as K into A into dou T dou Y, where Y is the uh, spatial coordinate in this direction. So okay, so this dou T dou Y now can be simplified as T minus T infinity, some temperature difference divided by the length scale over which this is happening. So now if I now take this here and write this as HA T minus T infinity and cancel out A and this temperature difference, then I'll get HL by K. So this itself is a dimensionless form of H. So H is the dimensional form, whereas this HL by K is the dimensionless form. So there goes one. Now let's take a look at two, dimensionless temperature gradient. So let's non-dimensionalize this problem. So where we have something like HA into T minus T infinity divided by K A into dou T by dou Y. Now what we will do is we will first non-dimensionalize the length scale. So y star, the length. So non-dimensional length would be y by L, where L is the characteristic length scale. And let's say we will write down a non-dimensional form of temperature as well, which can be something like T minus T infinity by TW minus T infinity. So yeah. Okay, so let's get rid of these two A's first, and I'll have H. I'm taking this to the right hand side, so I'll have K, and if I multiply and divide by L, so I have some L over here, and this dou Y becomes dou Y star, and this T should become dou theta star. Now I know that there's a W missing somewhere, so I should cast this problem in a different way. Okay, this itself is TW minus T infinity, and so if I have a solid which is at TW, there is some T that we're interested in, and T infinity is the temperature over there. There is a T gradient at the wall, which is dou T dou Y. This is the difference for convection, and anyway, I'm not being able to get the math right over here, but essentially there should be another TW coming in over here to match this. But anyway, so if I now take KL on the other side, uh, sorry, I'm not doing this correctly. Give me a moment. So let's go through the lecture slides once. Here we have this. So my slides are visible, right? Okay, so this is how we got it. So dou T dou Y can be cast in that way. Okay, got it. Okay, let's go back here. Okay, so convective heat transfer is nothing but H into A into T minus TW minus T infinity, and that should be equal to the conductive heat transfer, that is Ka into dou T dou Y. And now let's say I'm writing a Y star as Y over L and theta as T minus T infinity by TW minus T infinity. These are my two non-dimensional quantities, and I'm writing what T dou T dou Y should be in its non-dimensional form. And okay, so from here I can say that T is equal to theta into this thing, into this temperature difference, minus T infinity, right? So if I now simply derive this with respect to Y, what I'll get is dou theta, and I'll do this with Y star. So dou Y star into this minus T infinity will become a constant and won't show up, and Y is equal to Y star is equal to Y by L, so we should take that into account as well. So this will be divided by L. This is what dou T dou Y is. Now casting this back into this form, so I'll have H into A into this equal to K into A, and instead of dou T dou Y, I'll write down this new form that I found, which is this temperature difference divided by L, I take this out, take the A out, and now if I write dou theta by dou y star, then that is h into L by k, which is nothing but my Nusselt number. So that's how option A is correct, and option B is also correct, and option C simply put these two things together. So Q equal to HA into this temperature difference, that is the convective heat transfer, and Q equal to this Ka into dou T dou Y, that is the uh, conductive heat transfer. If you take a ratio of those two, then once again you will achieve this form. So we will get the Nusselt number back once again. So dou T, if I replace with this temperature difference and Y with L, and we take these out, we will again get back H into L by K. So it's option C as well. So the correct answer should be all of the above. Hope that makes sense, and I'm sorry got diverted a little bit in between. Any questions on this? Okay, so I hope I could make myself clear. Now we'll move along. We'll move on to question 4. It's a simple one asking us what topics are of relevance to, or convective heat transfer is of relevance to which topics? Is it option A, electronics cooling, option B, refrigeration and air conditioning, option C, industrial power generation, or is it option D, all of the above? Okay, so quick response is in favor of option D, and it is indeed correct. We know that these are all important areas where heat transfer becomes important. There are countless other examples as well. So that's why studying this makes sense. We are not wasting our time here. I hope we are convinced of that. Okay, so we'll move along to question number 5. This is a match the following type of question, which is telling us which has two different physical quantities on the left hand column and units on the right hand column. So you'll see that there are two options on the left hand column and 4 on the right. So they'll have to uh, each of these two will match with any of these 4 options. So once you have figured out the correct combination, you can see that there are 4 options given below as well. Option A, A1, B4, option B, A4, B1, option C, A3, B2, and option D, A2, B3. And once you have figured out the correct combination, you can either type in the chat box or unmute and let us know what you think is the answer. Okay, we have two responses, one in favor of option C and one in favor of option D. So it's either A3B2 or A2B3. So we're sticking to 2 and 3. Okay, so one of our options got changed to D again, not C. So let's see if it's correct. It is indeed correct. So conductivity K has, we can find this from our equation of Q equal to Ka into dou T dou Y. So if I just put the units now, so Q is in watts, that is joule per time, equal to K, let's keep it as it is. A is m square and dou T dou Y, so I have temperature up top and length scale down here. So 1 m would cancel out and the units of K would be watt divided by meter into Kelvin. So watt per meter Kelvin, option 2. So A should be matched with 2. A2, that's correct. Then again, we have to find out for H. So this is again Once again, we'll follow the same procedure. H m squared. This is K. So simply H equal to watt per meter square Kelvin. So option B should be 3. So A2, B3. Option D is the correct. Any questions on this? So hopefully not. We'll move along. Now this is a numerical type question. It is asking us to consider the figure shown below, and given that there is a heat flux of 80 watt per meter square. So heat flux is rate of heat transfer per unit area, Q by A, and that is given as 80 watt per meter square flowing through the slab, and T2 is at 300 K. So this T2 is at 300 Kelvin, and dimensions of the slab are so L equal to 0.5 meter. L is the thickness of the slab. This is 0.5 meters. The area of the slab is 1 meter square. The thermal conductivity K is given, that is 0.8 into watt per meter Kelvin. All we have to do is find T1. Should T1 be option A 305? These are all in Kelvin, by the way. 305 Kelvin, 400 Kelvin, 350 Kelvin, or 320 Kelvin. Okay, we have one response in favor of option C, that is 350 Kelvin. There's no hurry, take your time, and once you have correctly solved this problem, you can type in your answer in the chat box. So there is no heat transfer and there is no heat generation in this slab anywhere. So, the Q can be written as K into A into dou D dou Y. Now, in the absence of any heat generation, we can assume that within the entire domain. So let's not call this Y, let's call this X now. So if this is my slab, this is at and this is my x-axis. This is x equal to 0, this is x equal to L, and so on. So in the absence of any heat generation, we can assume that, we can not assume, show that temperature variation within this slab will be linear. So if there is some T1, there is some T2, the temperature difference in that case will be T1 minus T2 divided by L, or the temperature gradient can be written like this. And this gradient would be the same all across the wall because the temperature is linearly varying. So now if I take Q by A, so A I'm taking on the left hand side, equal to K. Okay, so we have one response in favor of option B, 400. Let's work through the problem and let's see. So it's equal to K and dou T dou X, sorry, not dou T dou Y, dou T dou X. Now I can replace with T1 minus T2 divided by L. Now we simply plug in values. This Q by A is equal to Q double prime, that is the heat flux. And anyway, if it is heat, we had been concerned with heat transfer rate and not flux, then we could have plugged in this value of A anyway. But that's not required here. The heat flux itself is given in watt per meter squared. So we will put 80 equal to K. Now K, value of K is also given, which is 0.8. T1 is yet to be found out. T2 is 300 and L is 0.5. So if I'll just take this on this side, and this will be 800 by 8, which is equal to 100. So now T1 minus 300, and I'm taking this 0.5 also on the left hand side. So 0.5 into 100 gives me 50. So this is equal to 50, and T1 finally should give me 350 Kelvin. So it should be option C, that's correct. Let's have a look at the solution. It is indeed 350. Okay, any questions on this? Was the process in which we did the uh, calculation clear to everybody? Okay, so let's move along. We'll move on to question number 7 now, which is asking us select the law that determines the radiative heat flux for a body. Is it option A, Stefan-Boltzmann law, option B, Planck's law, option C, Kirchhoff's law, or is it option D, Wien's displacement law? Okay, so we have two very quick responses in favor of option B, Stefan-Boltzmann law, which is indeed correct. So can anyone tell me what this law looks like? So we are looking for the radiative heat flux of a body. What is this equal to according to Stefan-Boltzmann law? Can anyone help me with it? What should I write here on the right hand side?
Stephen Boltzmann constant multiplied by temperature raised to 4.
Temperature raised to 4. Correct. So there's actually, sorry, this is usually the Stefan-Boltzmann constant is given by sigma, and there is often this epsilon associated with it, which is the emissivity. So this is emissivity. This is a property of whatever surface we are talking about, emissivity. And Stefan-Boltzmann law, the value, it is a constant which has a very nice number, that is 5.67 into 10 power minus 8 and t raised to the power 4. Okay, so this has a unit as well. So the unit of this should be heat flux divided by Kelvin to the power 4. Right? Yeah, sounds right. Okay, so that is the Stefan-Boltzmann law. Any questions on this? not, we'll move on to question number 8 now. So we have two figures that we're looking at here, and the question is telling us that among the two figures shown below, identify whether they depict an external flow or an internal flow. So there are two figures, figure 1 and 2. You have to match which one is an internal and which one is an external flow. The two options are A and B. Is one is internal flow, two is external, or one is external and two is internal? Okay, so seems that we agree that option B is correct. Figure 1 is external and figure 2 is internal. So evidently so. So that is indeed correct. And here in the first case where we have a cylinder like this and there is a flow around it, it's only the flow that near the body that matters. And one important thing is that we will assume that this body of fluid in which this solid is immersed is actually infinite. So doesn't matter in which way I go. Sorry. Uh, So it doesn't matter in which way I go. So it seems like I can't draw there. If I go there, then the slideshow is stopping. So anyway, so this is what it looks like, and it's an infinite expanse of fluid. So it doesn't matter in which direction I go, I will keep finding more and more fluid. That is the assumption under which we solve for external flows, which this is an example of an external flow. We will go through in detail of many cases. The one very important case would be that of a boundary layer flow, in which I have a surface like this and an infinite expanse of fluid above it, and we will find out what happens, how the boundary interacts with the flowing fluid and develops some certain flow features known as boundary layers. So we'll go through details of them later. And in the second one, you can see that there is a boundary shown here in gray, this one and this one as well. And we are looking at a flow confined between these two boundaries. So these cases, they are known as internal flows. The flow is happening internal to a certain number of boundaries. So that's the feature of an internal flow. We will look at certain cases of internal flow as well. This, for example, figure 2 is that of a channel flow. We will look at pipe flow as well, in which I have a circular pipe like this, and we will look at what happens when some liquid or some gas, a fluid for that matter, flows through this pipe and interacts thermally as well with this pipe. Okay, any questions on this? If not, we will keep moving along and we will come to question 9 of today's session, which is again a match the following type of question. It is asking us to match types of boundary conditions with their mathematical expressions. Now, these are generic mathematical expressions given here. Uh, you can think of them as certain examples. So, which option from this right hand column is an example of a boundary type given in the boundary condition type given in the left hand column? So there are 4 each, and each of them will match with one option, and we have certain combinations in the options given below. So try to match them first and then see which combination, whichever combination you end up with, whether you have that within the options given below or not. So the boundary type conditions are 1 Dirichlet condition, 2 Neumann condition, option 3 Robin boundary condition, option C Cauchy boundary condition, and there are these mathematical expressions as well on the right hand side. So option A says it's dou I dou x equal to some function f. Option B, y equal to f. Now f doesn't have to be a function, it can be a constant as well. But anyway, so I've written f so that it's general. And option C is C1y plus C2 dou I dou x equal to f. Here C1 and C2 are constants. And option D is y equal to f1 and dou I dou x equal to f2. Okay, we have one solution in favor of option C. That is 1A, 2B, 3D, and 4C. Let's see what others have to say. Okay, so let's have a look at the solution. It's actually option B. So let's go through each of them first. We will try to match these first. So first of all, Dirichlet type. Sorry. So first of all, Dirichlet type boundary condition is one where we explicitly mention the value of any variable on the boundary. So if I have a, let's say, a solid slab like this, if I say that the temperature on this boundary is equal to some PW, this is an example of a Dirichlet type boundary condition. So one should match with B, where y is equal to f. The exact value of y is mentioned at some boundary. The next one, Neumann boundary condition, is where we say things like, let's say, the dou t dou y on this is equal to something. So it could be like q divided by k into a. So where gradients of the variable that we're trying to solve is mentioned, then it's a Neumann type boundary condition. Where an example is given here, dou y dou x is equal to f. So the gradient of y is given and not y itself, which should have been given in case of a Dirichlet type boundary condition. One see one example of Neumann type boundary conditions can be seen in symmetry planes, where let's say if I'm trying to solve some fluid flow or heat transfer problem through a cylinder which has an axis of symmetry like this. So in that case, in that plane of symmetry, I will say that dou y dou r is equal to 0. So these are known as zero Neumann boundary conditions. This is true for many flow cases as well, in which, let's say, if flow is coming in through here and leaving through here, and if it's sufficiently long enough, I can assume that the outlet, at the outlet, all the uh, gradients, so if this is x direction, I can assume that all the gradients of all variables should be 0. This is also a valid assumption, and this also falls under this class of zero Neumann boundary conditions. It doesn't have to be 0, it could be anything else as well. Simply what it means is that gradients of some quantity is 0. That where if we are mentioning that, then that is a Neumann type boundary condition. So 2 should match with A, and sorry, 3 Robin type boundary condition is where a combination of both uh, the value itself as well as its derivatives are employed. So things like this. So let's say there is some uh, heat transfer through the solid going on here. So this Q should be Q equal to Ka dot E dot X, and on the outside I have another Q which should match with HA into TW minus T infinity. In that case, if I say that both these Q's are same, Q conductive and Q convective, in that case, this would simply boil down to Ka dot E dot X equal to HA, this temperature difference. So in this case, I can simply take it to the other side and say that, you know, some constant times there is some derivative minus or plus also doesn't matter into some constant into again the, so I won't say TW in this case, I'll say T, which is the temperature. So equal to 0. So this you can see resembles something like C1 uh, dou y dou x plus C2 y is equal to 0, or not 0, or you can say F as well. So this is an example of a Robin type boundary condition, and where these two things, one Dirichlet and one Neumann type, is mentioned separately but uh, together nonetheless, that is a Cauchy type boundary condition. So 4 should match with D. So if we take all things together now, 1 should match with B, 2 should match with A, C, sorry, 3 should match with C, and 4 should match with D. Right? So among the options given here, option B matches with it. So option B should be the correct answer. I hope things are clear. Any questions on this? All right, so if there are no questions, we'll move on to the 10th question of today's session, and the last one as well. So here some three options are given, three statements are given. You have to pick out which of these statements are correct, and then there are some uh, combinations given as options A, B, C, and D. So you'll have to pick that ultimately. So the three statements are: statement 1, free convection is caused due to buoyancy forces and density differences. Statement 2 is forced convection is driven by some external source. And statement 3 is, in general, heat transfer coefficient for free convection is higher than forced convection. So which of these are true? So option A says that 1 and 2 are true only. Option B says 2 and 3 only are the correct statements. Option C is telling 1 and 3 only, and option D is telling all of the above, which means 1, 2, and 3, all of them are correct. This does not mean that, you know, options A, B, and C are correct. It means the statements 1, 2, 3 are correct. Okay, we have one quick response in favor of, in favor of option A, 1 and 2 only. Let's hear what others have to say. Okay, so let's take a look at the solution. It is indeed option A, 1 and 2 only. So free convection is indeed caused due to buoyancy forces and density differences. So free convection has another name. Can anyone tell me what is it? Natural convection, correct. and there is forced convection as well, in which some external source is driving the fluid flow, which is causing convection to occur. So if I take a cup of coffee, which is hot, presumably, uh, if I just keep it like this, so then the uh, first of all the water of the coffee, it evaporates and it goes up since it is lighter than the surrounding air, and also the air around it heats up and that also moves up, and there is colder air the uh, from the sides which rush in to take its place, and this sets up these loops of airflow known as convection currents. So this is simply happening due to the density difference caused due to temperature difference, and that leads to buoyancy forces on these packets of fluid. So, and this happens naturally. There is no external source involved here. So that's why a mode of convection like this is called a natural convection. On the other hand, if I come in over here now and I'll remove this, and if I blow some air on top of it, I want to cool it down fast, then that is forced convection. So one important thing which I said is that cool it down fast. So essentially in most general cases, typically forced convection is the heat transfer coefficient, or the rate of heat transfer is much higher in case of forced convection than free convection, although there can be some you know exceptions to that rule, but typically this is the case. So which is why statement 3 is incorrect, but statements 1 and 2 are correct, and so the correct solution which you should have picked is statement option A, that is 1 and 2 only. Okay, any questions on this? So with that, we come to the end of today's session. Thank you all for participating. We will meet again next week at this time, and hopefully some.
Can I ask you a doubt?
Sure, yes, please do.
See, is this the discussion for last week?
It's pertaining to week 1. Yes. So yeah,
So the current week's lecture will be discussed next Tuesday.
next Tuesday. Yes.
So all the 12 weeks we will have discussion.
Yeah, and hopefully a 13th week as well.
Okay, well, okay.
Okay.
Thank you.
Okay. Thank you all. Good night, and we will meet again next week. And hopefully there will be more participants then. Okay. Thank you.